Yeah, I'm getting nervous.
Test, test, test. Testing, testing. All right.
Yeah,
Getting back into the groove.
There we go. Beautiful.
Test, test, test. Testing, testing.
All right.
Getting back into the group.
Everybody settled in. Thank you. Test, test, test. Testing, testing. All right. We got a lot of people coming.
Yeah.
Getting back into the groove.
There we go.
Everybody settled in.
Beautiful.
Thank you. Test, 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 testing. All right.
All right. Yep. You good? Everybody settled in. Thank you. Test, test. Testing, testing. All right. We got a lot of people coming.
Yeah.
Getting back into the groove. Ah, okay. That's what it was. Okay. The Global Breakthrough Energy Movement now presents to you the next speaker, Moray B. King, who is an internationally known physicist, author, and speaker with specialties in zero-point energy, Tesla technology, and quantum physics. He's the author of Tapping Zero-Point Energy, Quest for Zero-Point Energy, and The Energy Machine of Thomas Henry Moray. Now, Moray B. King is going to be interviewing a man that I highly respect and look up to, and I could easily do an hour-long presentation just to discuss this man's achievements. So without further ado, I'd like to bring Moray B. King up to present Mark Leclair.
Have the sound? Mark Leclair came into my life, I think, in 2011. I knew in my research for Brown's gas and everything else, there was a water cluster formed, but I had no idea what the structure was. And I knew that was going to be my next round of research to try to find out what that was. And then Mark Leclair calls me on the phone, I think, at the beginning of 2011. And when he explained to me the research he's been doing with cavitation and everything else, he had the form. What he discovered was the seed to what the water crystal form that could make the seed to a heavier than air's secondary gas in Brown's gas. And as a result, he connected all the dots, including observations of transmutation happening in some of these electrolyzer cells. And what Mark Leclair has an incredibly simple experiment that, frankly, I think just replication of his experiment will change the entire world, because he's discovered something incredibly, from a simple cavitation experiment, the ability to transmute, to have transmutation of elements. So without further ado, because I know Mark loves to talk and explain this, I'm going to introduce Mark Leclair. He has his both his bachelor's degree and his master's degree from Worcester Polytech Institute in fluid dynamics. Had a award-winning career at Lockheed. And when you see what he's discovered with his company at Nano, you're going to be thrilled, because I was thrilled. So let me present Mark Leclair. Let's put him on the screen. Let me present Mark Leclair. Technical difficulties. They're trying to put you on the screen, Mark. Can you hear us? Can you hear me? Do I have to entertain the troops? Should I tell you a story? I'll tell you a story. I'll entertain the troops. My wife has finally come to one of my
Yes, I
conferences,
can.
and she rarely doesn't like to come to the conference. She says, oh, she used to get invited to these science parties, and she says, oh, I hate going to those parties. I don't understand a thing they're saying. I just don't feel like I fit in. Well, I said, honey, fitting in is really easy. There's one word you can always say no matter what they're saying, and they will love you. And she goes, oh, what word's that? I says, that word is indubitably. And she said, but let me warn you, there's one word you must never say, for they will hate you. She goes, oh, really? What word's that? I said, that word is poppycock. I said, and she went, well, this kind of sounds like fun. I'm going to the party. So she jumps in the shower, and a few minutes later, I hear her singing, indubitably, indubitably, poppycock. And so we get to the party, and I'm mingling with the crowd, and I look across the room, and there's a physicist from the University of Utah writing equations on a pad of paper enthusiastically at my wife. Now let me tell you about my wife and equations. She does not do mathematics. She calls them hieroglyphics. And so I engage my group with conversations. A few minutes later, she comes back up to me. She says, I want to go home. I blew it. And I go, honey, what happened? It looks like you were just doing it beautifully with the physics professor. Oh, I was. That indubitably word worked really, really well. But when he started writing hieroglyphics, I just could not resist. So I tried the other word. Rest assured, she learned her lesson. At this conference, when she says indubitably, she really, really means it. Okay, I think we got you. Can we put Mark up on the screen? We couldn't get him on the screen? Oh, darn. They can't see you, Mark. Anyway, they have your Nanospire slide up. And do I change the slides? Yeah. Okay. And I'm gonna let you take it away from here. So go ahead.
Well, I'll just say hello to my audience anyway. Okay. Can you all hear me? How's the audio quality, Moray? Okay, I'm getting a delay in terms of the audio. Am I good? Okay. Oh. Yeah, I'm getting a significant lag.
Are you hearing your own echo?
Yeah, I'm getting about a 10-second lag from when I talk to when I can hear it back on the audio.
Okay, and that's probably why you're probably coming back through my microphone. Because that's why the echo is occurring. We hear you. If you just start talking, we'll be fine. Are you watching the live stream?
Yeah, I'm watching the live stream.
Okay, yeah, that's where the echo's coming from. So I guess turn off your sound
Turn off my sound?
on the live stream. Mute the
Okay,
live
one
stream.
second. Oh, from the live stream? Okay.
Okay, you can still
Let's
hear
see,
me.
how do I... Yeah, I'm trying to figure out how to use that right now.
Okay, you can tell me what slide is up if you want to close it, but I think all you have to do is mute it. Mute that particular video from the live stream.
I've never used live stream.
Okay. Right, he has this presentation on live stream. If you want, you can just, if you can't mute it, you can just shut it down.
Where's the... I'll just shut down live stream, but then I won't be able to actually see the slide.
Okay.
If you turn the camera that you've got towards the screen more, I might be able to see it.
Okay. Oh, there you go. Can you see it? Yeah, the mute button is the bottom right of the live stream. Okay. Okay, I can also, you can also tell me what's at the top of your slide, and I can make sure that slide is up. Can you see the screen?
Oh, I see the mute screen. Okay, there we go.
Okay, good.
Can you hear me still?
Yep. We're good.
All right, so can you hear me now?
Yep. We hear you fine.
Okay. Well, then I'd like to say hello to my audience. Pleased to really have a chance to be able to discuss my material. I always, like Murray says, always enjoy talking about this. Just to kind of point out what we're using here, we're playing with cavitation, and the cavitation bubble is shown right in the top center of the slide. And if you look carefully in the center, you can actually see a core coming down through the bubble. That's a liquid core of water. That's a steam bubble. It's approximately 1 millimeter in diameter, and it's collapsing next to a surface, and that produces an asymmetric collapse, which launches a jet towards the surface. So at any rate, Murray, could you hit the next slide?
Everybody read it quick.
Okay, I don't see the next slide coming up, so maybe there's a delay on the video too.
Really, there's a big delay between seeing this slide?
Yeah, I'm looking at the first title slide right now. Have you already advanced it?
I did.
Okay, well, let me just give it a second then, and it should come up on my end. Yeah, there's some sort of strange delay going on. Oh, yeah, I see it. Okay. So, yeah, I'm going to skip. I'm not going to actually read that, but I'm going to tell you in a nutshell that what's happened is that during experiments in 2004, I was doing machining with that jet that you saw on the title slide. And I have a sequence of patents which I use to form these bubbles and actually control the direction, the speed, and the size of these jets. So I was doing experiments that were very akin to water jet cutting. In the process of doing those experiments, I noticed a lot of the holes were actually not round but faceted, and came to the conclusion later on that it was actually a crystalline form of water forming at incredibly high pressures that are formed in cavitation that can occur during the collapse, can go over 500,000 psi. And this crystal that I discovered is actually an equilateral triangle subunit. So it's not a hexagon pattern like you see with ices. It's not ice. And it's actually covalently linked along the axis with OH bonds, a sequence of those. And in the plane, it's actually linked with the hydrogen bonds. So the thing is very strong in the axial direction, but weaker in the transverse direction. So it can actually peel apart, kind of like spaghetti, with like a bundle of spaghetti. The crystal typically would exhibit hexagonal cross sections, but some of the ones that I saw were equilateral triangles, and that's what led me to the conclusion on the molecular structure. When you work out the numbers on this, it turns out this is dense as steel. It's got a specific gravity around 5.5, depending on the lengths of the bonds and the compression. And so really the crystal is the crux of what led to the next discovery, which when I was in the process of doing the machining, I began to notice that long trenches were appearing on the material on the surface that I was using to collapse the cavitation bubble next to. And after only a few minutes of doing the machining, I take these things out of the water, and there's no apparent cause and effect why they should have appeared, but yet there they were. And so under examination under the microscope, once again, you could see that these things were very symmetric. They had half hexagonal bottoms to the trench. And so later on, I was able to conclude that it was the water crystal carving the trench with the crystal halfway into the page. And that's why you see a half hexagonal cross-section to the trench. So it occurs to me that, this thing was producing heat. And so back in 2009, we received a grant from Hub Laboratories, and we produced a cavitation hot water heater. And the goal with this project was actually to demonstrate that zero-point energy was actually the responsible driving mechanism for producing heat in cavitation-related experiments where excess energy had been seen, particularly in the ones where they hadn't seen radioactive release. And so the result is that cavitation was really the driver behind quite a few of the cold fusion processes, in my opinion, but I'll get to more about that later. So yeah, next slide, Murray. Okay. So yeah, we ran these experiments back in 2009, and that's kind of what I'm going to go through with the presentation. You'll be seeing various results, both radioactivity, you'll be able to see radioactive tracks in polystyrene plastic. You'll see Geiger counter data. You'll also see some other pretty amazing things too, like patches of diamond that appeared on the core, and these are all things that I'll touch on in the presentation. Yeah, let's go right to the next slide, Murray. That shows me something beyond the abstract. Okay, and it'll be up here in a second. So in a summary, that's what we've done is we've taken this water crystal and harnessed it to be able to produce energy. And I produced a lot of these trenches by trying to pack as many attractive, sharp edges on metal as I could into the core, because there's an electrostatic attraction between the water crystal and the surface, which I'll get to later. Yeah, there's a little background there. I see it now. Okay, so Nanospire, we started back in the beginning of January 2002, and actually slightly before that, it was a Foresight Institute conference back in Santa Clara. And I was surrounded by the venture capitalists that convinced me that I should start a company harnessing cavitation reentrant jets. So in the process now, we've received, that says 7 grants. We're actually up to about 9 grants that we've won now. We won the top award in nanotechnology in the world, actually, back in 2003, and I was flown to Tokyo to present in front of a crowd of about 50,000 people. And I managed to beat out the likes of all the Japanese trading companies and quite a few other premier groups in nanotechnology, so we were really pleased about that. And then also want to point out that we've got 4 issued patents. The patents are extremely broad. They've got a lot of claims, and they really cover a lot of territory in terms of what you can use reentrant jets harnessed in different ways. I guess I'd want to put out the common thread in all of them is I've created a new prime mover in being able to harness the reentrant jets. Yeah, that's my smiling face on the top slide there, and Serge Levitt, my executive vice president, down below. And I guess I'll start by telling you a bit about Serge's background, because you've heard some about mine. Serge is the founder of a cavitation processing company called 5 Star Technologies. They went on to spin off another company named Erosion. They were into cavitation nanophase material production. And Serge was actually one of my former bosses. I consulted the 5 Star back close to 20 years ago. And so Serge and I have worked together now for close to 20 years. And Serge really is one of the most knowledgeable people in cavitation in the world, in my opinion, besides some of the other people that we work with. And he's a real asset to Nanospire. I also want to point out that he was a co-discoverer of, during the fusion experiment too, that we were actually trying to show that there really wasn't that much fusion going on during the 0-point energy release, but it turns out there was. So it was a serendipitous discovery, and I just want to point out that, Serge is right there with me. We were testing the thing out, and, we'll get back to what ends up happening in the results, but it's pretty fantastic. Then give you a little more background about myself. Like Murray pointed out, I'm a hydrodynamicist, fluid dynamics by training, thermodynamics, heat transfer. Also studied quite a bit of atomic physics, and my master's degree was in nuclear engineering. I studied the fouling of nuclear steam generators at Alden Research Laboratory, where it's actually the 3rd oldest hydrodynamic research facility in the United States, founded back in the Civil War. My former advisor back there during my master's was Mahadavan Padmanabhan. I'd like to point out, and we're pretty honored to be able to say that Padu, which is his nickname, Padu had just won the hydraulic medal, which is the top award in fluid mechanics and civil engineering. Next slide, please. So yeah, Murray, you can just kind of like advance them in advance for me like that because of the lag, and that'll work out. Okay. So I'm not going to spend that much time on them unless I really need to.
Yeah, we'll be of like minds.
right? Yeah, I also want to point out that I worked in the fluid mechanics group at Lockheed Missiles and Space Company in Sunnyvale, California. I was there for 4 years, from 1989 through 1993. Worked on cavitation issues surrounding the launch of the Trident 1 and 2 nuclear missiles out of the submarines. I managed to win every award that Lockheed had to offer. I had commendations from the Navy, commendations from Lockheed. I managed to solve some problems that were long-standing, that had gone on for close to 45 years, that a very large community of hydrodynamicists weren't able to solve. So that's why I ended up winning the commendations. I really began to focus hard on cavitation after Lockheed. Then I also worked for a rotor stator company that I produced a cavitating rotor stator just about the same time as Griggs was putting out the hydrosonic pump. Only a few months later, I'd filed a very similar patent, but focused on producing nanophase dispersions rather than heat, but both cavitating rotor stators, and both filed almost within a month of each other back in 1994. So, Murray, can you actually see the next slide yet, or?
What is cavitation?
What is cavitation?
Yeah, that's what's on the slide right now.
Oh, okay, yeah, no, it hasn't come up yet, so I'll just give it a second. In fact, you know what, I'm going to bring up my presentation on my end so I can actually see it and talk to it while we wait anyway. Let me see. So the next slide is actually the cavitation reentrant jet patent slide.
Right.
Is that what you say?
It's the Larry Crumb's photo and the wiki photo of the cavitation collapsing bubble launching the reentrant jet.
Okay. All right. Yeah, I can see that on my side because I've got the PowerPoint here for me to look at anyway, so I'll know which slide we're talking about until it comes up. Yeah, let me point out exactly what's going on here, because this process is really key. With cavitation, it's nothing more than a boiling phenomenon. Cavitation is another word for boiling. So what you're doing is you're forming the boiling point, but at room temperature, by using very high pressure drop typically. Now, these cavitation bubbles can vary in character quite a lot from the boiling of a bubble that you would see in a teapot to the type that are formed by a laser, where they're very highly evacuated and they have very little water vapor on the inside of them. They're very dry. And that makes a big difference in terms of the collapse mechanics, because there's a lot of vapor in that bubble. It acts like a spring. And when it goes to collapse, it can soften the collapse. So cavitation then has very little water vapor inside the bubble. It typically forms, at room temperature, it's not so saturated. Those collapse very violently, and the interface of the bubble is actually moving at the speed of sound of the liquid, which for water, that's pretty fast. It's 1,500 meters per second. All right, and so the jet is also moving at up to 1,500 meters per second. That's the top speed for this thing. So the Mach 4 that I refer to is actually the equivalent speed in air, so that's a bit of a misnomer. Just want to point that out. Now, if this bubble collapses within 6 fully expanded bubble diameters of a surface, it'll cause the bubble to collapse asymmetrically. That's what you're seeing on the bottom. And the bubble, as it tries to pull away from the plate, is being slowed down on the side closest to the plate, but not on the opposite side. So the result is the bubble turns itself inside out like a torus, and then launches the reentrant jet down through the core, so the water is being pulled down through the center of the bubble. And the result is that the cavitation bubble is a way of being able to create a high-speed liquid jet. And my insight was that if I had a flat plate beneath the bubble, then the jet would always go 90 degrees towards the plate. I place a hole there, and the jet passes through the hole, and now I've got a aimed cavitation reentrant jet that I can do things with, like do machining, that sort of thing. So you can move to the next slide, Murray.
Okay.
Okay. I'll pop it over on this one too. Let me see.
Yeah, you have your own. Just keep going.
Yeah, I'll just keep going. Okay. So now you see the cavitation collapse sequence. Is that correct?
Yes.
Okay. Now, I basically have two classes of patents, one which I call the orifice patents, and the other the double bubble patents. Primary difference is I'm using a plate to slow down the collapse of the bubble on the orifice style patents. And the double bubble patents, I'm using another cavitation bubble that's collapsing in close proximity to aim the jet coming out of the other cavitation bubble. So they each have their kind of pros and cons in terms of doing nanotechnology, and like the one with the double bubble, you can actually place that in some very tight places, do machining in 6 degrees of freedom. Gives you a lot of flexibility. The orifice patent protects whatever the workpiece is against the implosion shock wave, which is about 100 bars of pressure, so it's pretty substantial. So the orifice patent is typically what I've used the most in terms of my research. I'll aim that jet down through a tube and I'll produce nanophase dispersions, that sort of thing. Next slide, Murray.
Okay. Product schematic.
Okay. Right. So now you can actually see some renditions of what I'm talking about. On the left, you can see that I'm using a lens to focus the light, and right where the focus is, that's going to precisely place the center of that collapsing cavitation bubble. So when I hit it with the pulse of the laser, it vaporizes right there at the center. It suddenly expands and then collapses, and as it collapses, it launches a jet down through the hole towards the workpiece. And then you can also see the double bubble version of that. I can actually sequence the formation of those two bubbles so they can be, in phase, out of phase. Got a lot of flexibility in terms of being able to place that. I can also do it with one laser and generate two bubbles with beam splitters. Next slide, please.
Reentrant jet micro nanofabrication.
Right. So that kind of gives you a background in terms of the space that Serge and I come out of. I mean, we were primarily nanotechnologists seeking to produce nanophase particles to be able to produce, both bottom-up and top-down fabrication technology to be able to, chew away holes, drill channels, that sort of thing, or actually do welding. I've welded silicon powder to silicon wafers through impact. Even from 3 inches away underwater, is able to hit the silicon with enough velocity to cause the two to fuse. So this gives you some general idea of kind of where we came out of. Fusion for us, really, it was a kind of a tangential move, but because it fell within our general expertise of cavitation, that's why we picked up on it. And for quite a few years, too, I've noticed a lot of, shall we say, irregularities in terms of excess energy with cavitating systems. I'd seen a lot of them reported, and I just want to point out that we don't claim to be the first to produce cavitation fusion. It's been produced by others for probably decades, and it'd almost be difficult to say who really was the first. Okay, so I just want to point that out. Our goal here was doing the nanofabrication, and then, the fusion and the crystal and all the other discoveries came up along the way, but really kind of threw a wrench in the works. So I had to revisit all of that to be able to get control of it again, to do nanofabrication. Okay, next slide.
Micro hole drilling.
Yeah, this is an example of some of the work that we did now. We were pretty lucky that we teamed up with the top nanotechnology university in the world, which is Albany SUNY, back in Albany, New York. And they've set up a consortia there at Albany that consists of about 20,000 members, a few thousand companies that are involved. Some of the notables include like IBM, Tokyo Electron, Applied Materials. And what they're doing is they've got MEMS fabs up there. I mean, they're teaching nanotechnology courses, degrees. We were one of the first startups that they actually teamed up with. And we did a New York State Energy Research and Development Authority grant together. And we did some machining. It was a repeat of some stuff that I had done previously with the Maine Technology Institute. And we wanted to see if we could gain control of this process to produce small holes in the zirconia disc for amperometric oxygen sensors. So what you actually see there are some examples of some of the very first cavitation machining that's ever been done. The hole on the left is only 20 microns in diameter. And you can actually see a little bit of the hexagonal pattern from a crystal impact on that one. Just want to point it out. The center picture is actually firing the laser through the moving free surface. I later on moved the lens into the water to get better resolution. And I went from my initial results were roughly 1/4 of a degree standard deviation with about a 1 1/4 degree accuracy, but that improved considerably to about 8/100ths of a degree when we finally did the New York State Development Authority machining. So if you look at the very bottom image there, that's a sequence of pits, about 200 of them, each of them about 7 microns in diameter. So the wonder in the line there is just the slop in the bearing stage that was used to move the workpiece. You can advance the next slide, please.
Nanomaterials processing.
Okay, so that's an example of what we're talking about. The diagram on the left, I'm creating the cavitation bubble in the chamber. I'm shooting the jet down through the narrow bore below that, and then I introduce whatever I'm going to mill in through the side ports. So it's a very simple device, but has tremendous flexibility and high uniformity. I mean, it's just amazing the results that we've gotten. I'm showing some of that on the right. That's actually zinc oxide, which I'd knocked down to an average size of 2.8 nanometer particle size. So there's only approximately 7 or 8 atoms in diameter, the particles were after processing. And just to point out, this is used in all the various industries that you see listed there. So high-shear manufacturing with cavitation has been around for a long time, actually, but this is the latest mousetrap, and it's pretty much poised to dominate the high-shear market. Next slide, please.
Nanospire grants.
Okay, so that's an example of all the various grants we've done. On the bottom, you can actually see we started off with Maine Technology Institute grants. And really, the very first one was a grant that was sponsored by the Maine Space Grant Consortium, which is part of NASA. And I was flown to NASA Ames in Silicon Valley, and I gave a presentation on my cavitation and original life theory. And it was really well received, and I ended up launching Nanospire. Pretty much that was the point right there. That was in July 2001, and I came back and did the Foresight Conference later on that fall, also in Silicon Valley. So that was kind of the beginning point. Then I did a series of grant applications, sea grants with the Maine Technology Institute, because here in the state of Maine, we're really well supported in terms of startups. From from the legislature, they endowed the Maine Technology Institute to give out everything from small grants to pretty large development grants as well. So it's been instrumental in getting the company off the ground. I'd like to thank the Maine Technology Institute. And then also, you can see that the New York State grant that we did, the nano fabrication. And by the way, I want to point out that the professors that were associated with that, particularly Eric Eisenbraun, is a real believer in terms of what happened. I mean, this crystal was causing all sorts of crazy behavior because it has an electrostatic charge on it. The crystal is very highly charged. It's mostly positively charged. And it had a mind of its own. And, we'd be sitting there trying to put a hole in the center of an object, and instead it would carve a trench around the outer perimeter of the thing. So Eric is a real supporter, and he knows that the Leclair effect is quite real because he's seen it for himself. And so the Albany Nanotech Group, I can tell you, they're real highly regarded throughout the world in terms of prestige for nanotechnology. And these guys are willing to be able to put their name behind what we saw. So, to some degree, they're also, they were the first professors to actually ever see the Leclair effect at work. Just want to point that out. So thank you for their support too. Then I also did another MTI grant, which was just to prepare for a SBIR that we applied for. And then also the grant that we did with Hub Laboratories, that was back in 2009. I want to point that out. That was actually very instrumental in terms of launching this entire thing because, that got the whole process going, but it didn't end up so well in some regards, which I'll get to later. But yeah, there were some bad things that happened during that experiment, which I'll get to beyond the fusion itself. Then also I want to point out that last fall I get to present as an invited speaker to the water conference. It was actually called the Physics, Chemistry, and Biology of Water. And I covered a lot of the same material, which is in these slides, but I've expanded it dramatically. But I'm going to repeat some of the slides I gave at that presentation as well because they're relevant and I think you'll find interesting. Next slide, please.
Cavitation, erosion, and fusion.
Okay, so in the process of doing cavitation machining, the big question comes up, how deep is the hole going to be if you know the characteristics of the jet? how deep is the hole going to be depending on the material properties. Now, it seems like that might be a trivial thing to solve, but it turns out that people have been trying to investigate that phenomenon and come up with a general equation that's applicable to all materials for about the past 100 years, starting with Lord Kelvin. And they've all been highly unsuccessful. I mean, most of these equations are good for narrow ranges of certain materials, but not generally applicable. I developed an equation that predicts cavitation erosion incredibly accurately for all materials. And in the process of doing that, I came up with the insight that there's a very thin layer right at the impact where the jet, which is shown in blue on the left, strikes the material. And the red zone is a zone where van der Waals repulsion goes crazy. I mean, it goes up with the 6th power of the separation distance. So when you begin to squeeze a material like that, it turned out that there was actually a large component that was due to van der Waals repulsion. So I wrote an equation which includes the effect of the repulsion energy, and then behind that, it treats it with a more classical impact equation approach that's used in mechanical engineering. And by combining the two of those, the quantum part of it from the repulsion, and then the more classical approach, I was able to derive a general equation that fit 22 different materials that were determined by the American Society of Testing Materials. Next slide, please.
Redefines cavitation erosion.
Yeah, so what you're seeing on the top chart is actually 22 different materials that were tested for their cavitation erosion resistance. Okay, and so the blue dots are actually my predictions, and then the red crosses are the actual data for those materials. So what you see is a range of cavitation resistance going horizontal. That's typically the difference between a soft alloy and a hard alloy for different materials. For instance, all the way to the right, you've got very high cavitation erosion resistance. Those are typically tool steels, stellite, very hard materials. And the materials on the left have low cavitation resistance, things like copper, bronze, that sort of thing. Okay, and so I'm not sure if you can actually read some of the quotes here, but every attempt in the past has basically failed miserably. So this is really a huge coup, being able to predict cavitation erosion. And the reason this is even being brought up is because the pressure and temperature of impact can be predicted by this equation. And so you can actually determine the thermodynamic equation of state. And it turns out for a lot of the hardest materials and the highest speed jets that you're going to achieve borderline fusion conditions just during the impact of the jet alone, even without having to invoke zero-point energy or the Leclair effect, which take over after that and begin to form trenches. Next slide, please.
Faceted cavitation.
Okay. Yeah, so this is an example of what I was seeing. The upper left corner, you can see there's some facets to that impact. It's largely hexagonal, and just below that, you can see a nice round impact for contrast. And below that particular picture, you can see a really nice impact that's hexagonal in aluminum. And of course, look at that equilateral triangle impact on the right. That's in paper, actually. I'm also able to launch the reentrant jets out of the water and through the air through a device that I put together. So I'm able to do machining and fabrication in air and not necessarily submerged. So that particular impact was a reentrant jet that had flown 7 meters across the laboratory and then impacted a paper target. And you can see it maintained the crystalline structure even after traveling 20 feet through the air. Next slide, please.
The water crystal.
Okay, so this is the gist of it right here. The crystal is able to link along the axis, like I pointed out, with OH bonds. But as you can see, the high pressure is compacting the hydrogen and oxygen into the tightest possible configuration, which, if you think of a billiard rack and the way the balls, stack up inside, they form equilateral triangles, because that's as close as you can put them together. So that's what's happening in the case of this water crystal, is it's actually squeezing the hydrogen bonds to the oxygen, so it's in a 90-degree configuration. So a hydrogen is pointing up along the axis, and another one points along the triangle structure that forms. And so this thing actually leaves a lot of exposed protons, and it generally has a positive charge like on the face and on the sides, but it has a negative charge on the bottom, which is where, you know, the OH bond is allowed to bind. The result is this thing can form a closed loop. And if you look at the upper two pictures, that's the water crystal is linked into a loop, twisted into a figure 8, and then embedded itself into steel. And when the crystal hit the steel, it shattered, and you can see a sequence of hexagons that form the image as it goes around the figure 8s. So then to show that the protons are being heavily displayed, I reasoned that there must be 0 pH. So I did the old cliche, I did the litmus test. So I aimed the reentrant jets at the litmus paper, that's the center pictures. And for green litmus paper, you could see a red impact, and under better examination, that was actually a hexagon. And to the right, the orange paper showed a purple impact. Both of those were indicators of 0 pH, okay? And so you can actually also see fossilized imprints of the crystal. The lower right corner, that's an imprint into paper. That's another one of the paper targets that was struck from 7 meters away. And you can see there's a very fat head in the upper right corner, and there's a long whip tail coming down below that and then curving to the left. And in fact, the picture on the left, you can see that also. There's a fat head with a hexagonal profile, a long whip tail, and there's actually a hexagonal bulb at the end of that. That's an imprint that was left when it buried itself into rust. You could actually see the imprint of the crystal. Next slide, please.
Examples of the Leclair effect.
Yeah, this is where the magic begins right here. I mean, this is the plate that I use to control the collapse of the cavitation bubble. So I'm launching the jet down through the hole. The zone surrounding the hole in the upper center picture, you can see the some of the anodized black aluminum has been burned away by the defocus of the laser. And so that's all that caused that. But if you see the lines going all the way across that plate from one side to the other, those are the trenches that were carved by the water crystals. So what's happened is that the bubbles collapsed next to the plate, launched a crystallized cavitation reentrant jet towards that hole, but then it turned 90 degrees and headed towards its induced negative electrostatic charge on the edge, and it headed 90 degrees towards it, the path of least resistance. And you can see several of those occurred. The close-up pictures on the left, you can see that the trench starts off narrow but actually becomes wider in the direction of motion. So that was the first indication that this thing was actually starting to gain a head of steam with no apparent input. Now, if you look at the center lower picture, that's one of the crystals that actually chased and tried to link up with its tail, and it formed a perfect circle as it carved the trench going around trying to link up with itself. The picture to the lower right corner, those are half hexagonal trenches that were carved by the crystals inside the hole, inside the plate. And that's the hole that you see in the upper right corner and in the upper center picture too. Now the upper right corner picture, you can see some of the crystals have come through the hole. This is on the bottom of the plate that you can't see. And you can see that several of them have actually gone into orbit around their own induced negative charge on the edge of that hole. That's what they're doing. They're positive. The edge of that hole is negative, and it's orbiting it just like moons would a planet. So pretty bizarre behavior. You know, that was the beginning of it right there. Next slide, please.
Spiraling Leclair effect crystallized reentrant jet.
Yeah, so not only can the trenches form nice even half hexagons, but some of the time you'd actually see the jet spiraling as it formed the trench. But the idea is the same. The axis of the jet is actually flush with the page into the material. So the crystal is half out of the copper and half into the copper. And as it rotates, you can see the diagonal impact marks that it makes as it does it. Pretty amazing. Next slide, please.
The Leclair effect.
Okay, so this is what it comes down to. Like, if you look at the lower schematic that I'm showing, the crystal is halfway down into the page. And the reason for that is because as it's attracted towards the surface, the electrons are pulled up on the surface. And so it tries to get as close to them as it can, forming a least potential energy state, right? So if it's down too deep into the material, it tries to go up to the surface where the electrons are. If it's too far above the surface, it tries to go down into the material. So the place where it's as close as it can get is with the axis of the crystal flush with the material. Now, that crystal is coming out of the cavitation bubble at supersonic speeds, so there's a bow shock wave surrounding the crystal. And that's for certain. And I've actually seen images of the shock wave, Mach lines, these sort of things that are known to fluid dynamicists. You can see Mach fans. I mean, strong proof of, the supersonic speeds that are being encountered, okay? Now, as the shock wave is traveling through either a liquid or a solid at thousands of miles an hour, it's actually incandescent. So it's melting the material in the trench. And the positively charged crystal is electrostatically attracted to the negative shock wave, because the shock wave, as it incandesces, thermionically emits electrons. And then the powerful electrostatic charge of the crystal attracts all the free electrons on the surface of the plate, and they begin to stream towards the crystal and go skating past either side of it. In fact, on the previous picture, you could actually see the crystal is like a street, and the sidewalks on either side are where the electron flow was going past the crystal. So the result is that this thing accelerates, and it's got a runaway acceleration involved with it. And the zero-point energy portion comes in because there's a vacuum between two conductive surfaces, the front surface of the crystal and the surface of the shock wave itself. And they're in very close proximity, on the order of microns and down into nanometers. So that satisfies the condition for forming what's known as a quantum harmonic oscillator, where the electron cloud and both are actually moving in sync with one another. And that generates a net positive attraction at all times, because what's happening is that any particular atom at any time is not exactly electrically neutral. The electron cloud tends to fluctuate in position around the nucleus of the atom. So at any given instant, it's actually partially polar. And the Casimir effect arises because the partially polar nature of these things is in sync with each other. This is what Moray likes to point out as being coherence. So these things are acting coherently on a large scale, and the result is that the attraction is really strong. And in fact, there's really two forces pulling on this crystal, both ordinary electrostatic attraction and the Casimir effect, which is a form of electrostatic attraction, like I'm pointing out. The zero-point energy fluctuations are because as the position of that electron cloud moves around, it's causing a net attraction, but it's not depleting the energy of the system like you would expect from thermodynamics, namely the temperature is not dropping, okay? The other thing that's happening in this case too, and this is from observation, is, like I said, this thing is accelerating without bounds. And as I began to dig deeper into this, it turns out that there's strong indications that it was hitting relativistic speeds in very short distances, like on the order of millimeters. Okay, so I think I'm going to touch on a little bit of theory here that I've come up with in terms of what's propelling this thing. But I believe the high pressure on the front of the shock wave is packing the material into quantum wells, namely, you're right up against the van der Waals radius of all the surrounding atoms that are along the front of this thing. And so the result is that you've got a sheet of atoms that are packed so tightly that they can't move in any particular direction. They're right up against their neighbors. And the result is the Heisenberg uncertainty principle now says that these particles that are on the bow shock wave are fixed. And anytime you have a fixed position, you have a random momentum is being imposed. And the more fixed the particle is, the more random the momentum fluctuations become. So in the purest case, if you have a particle that's perfectly fixed, then it won't feel any force from any direction. It'll always respond randomly in terms of its fluctuation, but it won't feel any imposed force acting on it. And so what I've reasoned is that the electrostatic attraction and the Casimir force that are accelerating the crystal, it's a one-way street. The bow shock pulls on the crystal, but when the crystal pulls on the bow shock particles are fixed. They respond with random momentum fluctuations, and the result is Newton's law is violated, okay? That equal and opposite reaction here just doesn't apply. It's in direct conflict with a fixed particle that's behaving according to the Heisenberg uncertainty principle. So this is the heart of what powers what I call the Leclair effect, what powers the acceleration of this crystal. And that's really the gist of the Leclair effect right there. Next slide, please.
more on the Leclair effect.
Right, so if you see the particles are all packed up on the shock wave, they're right up against each other, so they can't really move quickly either in the plane of the shock or normal to the shock in the 90-degree direction. Like if you look at the little diagram I've shown on the lower right, the upper part of that diagram, one particle strikes another and then it moves to the right. That's Newton's law. But if a particle strikes a particle that's fixed, Heisenberg's principle says that the direction and the amplitude of the response are going to be random because it's a fixed particle. So it really doesn't matter what the imposed force is, whether it's from gravity, whether it's from flow resistance going past the outside of the shock wave, whether it's inertia. I mean, I've got strong evidence that inertia was heavily erased during this thing, and that's what allowed it to accelerate to crazy speeds in the first place. It took me a while before I came up with that, but I went back and ran the numbers, and it turns out the thing accelerated at something like 10 to the 30th Gs, and yet maintained its crystalline shape. Very strange. So implication is that no material object would have withstood that kind of acceleration of being ripped to shreds, but this thing did. And it also survived all sorts of other really energetic behavior, like small supernova explosions, which I'm going to get to a little bit later on. I just also want to point out that there's other types of phenomenon very similar that apparently may be propelled by the Leclair effect also. That includes like ball lightning, which has a tendency to just sort of drift around and meander. It can pass right through walls and windows that are shut without losing its form. And I believe this is a case of the force erasure by the Heisenberg principle. That's the same thing that powers the Leclair effect for acceleration. Also, EVO charge clusters that Kent Shoulders had discovered were also showed evidence of being propelled too. They left tracks. And charge clusters like the Proton 21 group, they saw some interesting effects with those too that may be related. So I just want to point out that the Leclair effect seems to pop up in some really interesting areas. Also the Hutchison effect, which isn't listed here, I believe is another form of the Leclair effect as well, for those that want to look into that. Next slide, please.
Leclair effect and zero-point energy.
Okay, so this is the very first cavitation hot water heater experiment that I did, and this is back in March 2007. And what I did is I used a drill utility pump, which is like a 2-inch centrifugal pump, and I sent water into a PVC chamber that I had a rolled up piece of aluminum plate that has a hole pattern drilled into it in rows and columns. And the reason that I chose that is because knowing that the crystal was electrostatically charged, I reasoned it would be attracted towards all the sharp edges presented on that plate. And by coiling it up, I'd present a lot of sharp edges into the volume that you're trying to heat, so you'd get a lot of effect going on. And so after running it, sure enough, I could see trenches both inside the circles, along the rows and columns of the holes, along the edges of the plate. I even saw some figure eights, and it's hard to make out, but in the lower right corner of that drill plate, there's a figure eight that if you stretched it out end to end would probably be 3/4 of an inch long. And it chewed a trench all the way down the entire length of that plate, 3 feet long, caused severe melting and discoloration of the aluminum too. Next slide, please.
July 25th, 2008.
So the next thing that I tried to do is also, I took a coil of copper wire, about 6 feet of it, about 2 meters worth of wire, wrapped it up onto a glass pipette, put that into a water tank where I aimed the crystallized cavitation reentrant jets towards the tip of the wire, which you can actually see in the lower left. And then what happened is the crystal was attracted to the wire, followed the spiral wrap of the wire. If you look to the right, you can actually see narrow trench on the outer edge of the wire itself. It was about maybe 20 microns in diameter, but it ran the entire length of the wire, the entire 6 feet, and half of that wire was actually out of the water. Half was into the tank and half was out of the tank. So once this thing got going, it didn't even need to be surrounded by water anymore. Just the vapor coming off the melting copper was enough to propel it. So the Leclair effect can start in water, but it can actually crawl right out of the tank, just like the old cliche. Next image, please.
2009 Cavitation ZPE reactor.
Okay, this is where things really start getting exciting. Okay, this is the early experiments in July. We ran a series from July through August where we probably did maybe 10 or 12 hours worth of total experimental runtime with a bunch of different configurations. This one was actually a pool filter, and I removed the pool filter element, took some more of that drilled out aluminum plate and formed it into a coil that was the same size as the element and put it back in there. So now the cavitating flow is formed by starving the inlet of that pump, which is on the left-hand side there, raising water from a reservoir, which is lower than the eye of the impeller, which helps to lower the pressure going into the inlet of the pump to force it to cavitate. And then I choked the inlet of the pump also with the valve that's shown. And then I turned it into a bubble generator, and the bubbles, cavitation bubbles, were fed into that chamber where the plate was. And so same thing, you know, these things went zipping along the edge. And in fact, if you look at the picture all the way to the right, look how disrupted that edge is. That's like looks like a serrated knife now. And it's just a series of serrated pits. I mean, it really chewed the plate apart. And in fact, that core, after 30 seconds of operation, fell apart in my hands in 3 pieces when I pulled it out. I couldn't believe it. And if you look closely, like in the upper center image, you can actually see a ghost image of the whole pattern of the plate. Well, it turns out later under analysis, that's a diamond film that was caused by the reflection of the neutron flux coming out of this thing was so intense that it actually burned the whole pattern image into other parts of the plate in the form of a diamond. Some of them were really large, like the patch that you see in the center. That white patch you see was confirmed to be diamond by XPS analysis, by SEM-EDAX, and also by mass spec. And it contained every element in the periodic table all the way up to californium. Next slide, please.
August 24th and 25th.
Okay, this is the real landmark experiments. This is what was done with the Hub Laboratories grant. Same idea. We've got a pump. It's raising the water from a bucket that sits below the inlet. And this lowers what's called the net positive suction head of a pump. You're trying to get as low a pressure as you can before it even gets into the eye. So I use a narrow inlet pipe to force flow restriction that causes a pressure drop. So does the valve on the inlet too. I choke that to the point where it's almost completely shut. And then I just barely crack it open. So this pump is starving. And it's, instead of flowing at its normal 25 gallon per minute rating, it's only flowing at about half a gallon per minute, but it's heavily cavitating. And that cavitating flow is being fed into a PVC pipe that contains a rolled up piece of that aluminum plate. The drilled out plate is in that chamber. And you can actually see the blue lines coming off. Those are thermocouples that are located along the various parts of the core. And so I had this thing recording through a data logger as well. So I was getting temperature readings every second from 4 different thermocouples. Next slide, please.
April 12th.
Okay, so this is another experiment that we did at the Naval Research Laboratory in Washington, D.C. Now, I want to point out that on our board of advisors, we have a fellow named Ed Pope, who's a former naval intelligence officer. He's retired now. He was also a former professor of counter-terrorism back at Penn State University. And Ed's been heavily involved with cavitation too. In fact, is quite famous for having obtained the details on the cavitating torpedo, which the Russians had. And Ed actually spent a year back in the KGB prison, kind of was made an example out of by Putin when he was elected, trying to look tough to the hardliners. And so he ends up being bailed out of there after a year by one of the senators from Pennsylvania. So he went to bat for us, and he's very pro what we're up to because he understands cavitation, better than most people would. And so he managed to get us into the Naval Research Laboratory where we did a repeat experiment of the original August 2009 experiment. Okay. Now I want to point out the August 2009 experiment caused a 30-degree average temperature rise through the core of that reactor. And I was seeing 50 or 60 degree temperature spikes. You see the temperature data in one of the following slides. But, I saw similar things happen here with this experiment. In fact, one of the things that was different is I used clear PVC in this experiment. And the image of the hole pattern of the plate actually burned right into the clear PVC. That's the center left picture that you see. So that's a pretty amazing image right there. You take a close look at that and you can see that the places that are glowing are the edges. So the crystal is orbiting each of the holes. That's why you see the holes. And you can see that they're lit along rows and columns. So it's going from hole to hole, orbiting each of the holes and then zipping along to the next one. So those are the areas that are emitting radiation, and that's why you see that image burned into the plastic. Next slide, please.
Temperature history.
Okay, so this is the August 24th, 2009 experiment. Now, that reactor core was only 1 foot long and 1.25 inches on the ID with the rolled up plate inside of it. The temperatures that you see, T1, T2, and T3, those are the different colored traces that you see. So I turn the switch on the left and you see an instantaneous 32-degree Fahrenheit temperature jump as soon as we hit the switch. And it just started climbing after that because we're recirculating the water back into the fill tank. But you can see that each one of those spikes that are going up, some of the highest spikes go from the inlet temperature all the way to the outlet. I mean, they're close to 50, 60-degree temperature jumps. And they're very short duration, too, very instantaneous. Reason why is it turns out they're micro-nuclear explosions that are going on along the plate right on the very front of the bow shock. It's compressing the material so much that it's creating fusion right on the bow shock. So this is the really amazing thing that happened. The zero-point energy accelerated the crystal, but it accelerated to the point where it generated speeds that were generating fusion right there at the front. So we're talking hot fusion, the kind that occurs inside of stars, during core collapse supernovas, other types of supernovas. I mean, I can actually see the signature in the data. You're going to see this in some of the following slides, where you can see that the nucleosynthesis followed the exact pattern as it does in stars. Okay, but at any rate, just to readdress this, you can really see that the temperature climbs. So in a matter of 16 minutes, this thing was already up to hitting peak temperatures of 143 degrees Fahrenheit, starting at room temperature. So, I mean, no having to wait for palladium to be conditioned, waiting 2 weeks for your electrolytic cell to start acting up on you. This thing is, you hit the switch and it produces energy. And it did it every time. We did 12 experiments and the results were the same, basically for all of them. Next slide, please.
Geiger counter data.
So this is a collection of all the various radiation data that we've collected. The most interesting one, the green curve that you see on the top, was actually an experiment that I ran for 5 minutes, came back 2.5 hours later, and noticed that the thing was radioactive as the dickens. And so I ended up hooking up the data logger for the Geiger counter, and I captured the decay curve. Now this is really landmark because, let me tell you, the PVC, the number one radiation absorbing element in the PVC is the chlorine. Turns out that it's got a neutron absorption cross-section that's thousands of times higher than the carbon and the oxygen. All right, so chlorine is extremely absorptive of neutrons. And what ended up happening is the 35 and the 37 chlorine ended up being converted into 39 chlorine, which has a 56-minute half-life. Yeah, 55.5 minutes. And you can see plainly those are the various half-lives. That decay curve is the result of a 56-minute half-life decay. So there's proof that a neutron flux came out of this thing, the chlorine absorbed it, and then re-emitted it as gamma rays, which the Geiger counter was able to pick up. And so, during the experiment, it was probably running like 50 or 60 times above the background level, because the background was never more than about 20 or 30 counts per minute. The other experiments that ran also showed radioactive release, but nothing close to that particular experiment, which was a special design that I won't get into for proprietary reasons. But yeah, it produced some pretty intense radiation and kind of hard to argue with. I mean, it's a lot more than you could say it was due to background or noise or scatter, so pretty in-your-face radiation results. Next slide, please.
August 24th.
Well, it turns out that I had this plastic dish, which used to be an electrical tape dish that was sitting in the metal desk that the reactor was sitting on top of. So the radiation from the reactor, the prompt radiation while it was operating, produced these rings of radioactive tracks in the polystyrene plastic. And I believe the reason it was rings is because they were charged particles, and they were just orbiting some sort of induced charge on the inside of the plastic. But pretty amazing. It ended up marking up the plastic as much as it did. And in fact, close-up of that plastic under the microscope, if you look at like the bottom right image, that one's really striking. I think what you're seeing there is both fusion and fission that happened side by side in the plastic. The upper image is a fusion release, which is exothermic. And then the lower one is actually fission, where you can see the nucleus is split into various fragments. Each one's a deuteron. That happened to be an oxygen atom because there was a total of 8 double tracks leading away from the main track, so I concluded it was the oxygen in the plastic. Next slide, please.
Mark, they want you to speed up the pace. We're running out of time.
Okay.
Nuclear track.
Now so here are the nuclear tracks in the plastic. You can actually see branching gamma ray tracks in the upper left corner, and that's because you get electron-positron pairs that are forming. You can see spiraling particle tracks. You can see collisions. If you look in the upper right picture, you can see that the material, this is all transmuted material that came out of the inside of the reactor. And these chips are on the order of maybe a millimeter in size. And they were spalling tracks that were being dragged along by the magnetic fields of these particles that were being emitted. So you see straight line tracks on the top of the dish, and into the plastic you see the nuclear tracks. Next slide, please.
Transmuted material.
Okay, so here's close-ups of the holes, and you can see, like in the upper left corner there, the crystal went from hole to hole, so it went partway around the circle, went to the next one, cut right into the material as it went. Some of these that orbited the holes left a whole bunch of transmuted material. That's what you're seeing in the center picture. But those chips, those white chips, came out of the holes. The other pictures you can see too that it formed at various thicknesses. Also, plate-like material formed on the surface of the thing. That's that green particle you see. That was mostly copper, zinc, and some lead thrown in. But if you look really closely, too, you can see it has a bubbled, textured surface. And I think that was from transmuted gases while it was molten were causing a bubbly surface. Next slide, please. So there's more examples of the transmuted material. I sent this around to various people to be analyzed. So I did redundant SEM analysis. I also did laser ablative mass spec, and I did XPS, which allows you to distinguish the binding energy, so we were able to pick out a diamond when that occurred. So I did SEM analysis at the University of Maine with also with Ed Storms and Media Sciences, a company that was run by a friend that had access to a SEM. And then I sent out the mass spec to Evans Analytical, which is the top laboratory in the United States for doing mass spec analysis. They were recommended to me by the University of Maine. And so we'll look at the results in the next slide.
Majority of transmuted material.
Yeah, so you're looking at actual diamond close-up there. It came in both a fiber form, which is really amazing, and also as a glaze. And in fact, the glaze, you can see there were some bubbles inside the diamond that ruptured. You see the little holes there that was emitting transmuted gases. And so the SEM analysis showed that was basically close to 100% carbon, other than the impurities that are, from the other elements that were produced. And then that spike that you see all the way to the right is the XPS analysis. That large spike is diamond, and the small spike just to the right of it is ordinary carbon. So that's how you can distinguish the two. Next slide, please. That's just an example of some random snapshot of some of the SEM analysis, some of the particles. You can see spikes forming at all the different elemental locations. Typically all the way up to iron and slightly beyond, you see a lot of that, just like stars tend to produce up to iron in fusion. Next slide, please.
From blue chip.
Now this is so that blue chip was the picture of that greenish blue chip that you saw with the bubbly surface to it. If you look closely, I mean, there's some pretty heavy elements there. There's lead, there's polonium. There's a lot of other things that just aren't naturally occurring that were present in that material. Next slide, please.
Particle analysis.
Okay, so that's the XPS analysis. It's a different part of the spectrum away from where the carbon was, but you can see that that also detected all different types of elements. Next slide. This is the mass spec data, and you can see that it was detecting all the way up as high as 6 transuranic elements past uranium. So you can see berkelium, americium, plutonium, californium. I mean, these things are not naturally occurring. There's also short-lived isotopes like promethium that was detected. It has like a 2-year half-life. So pretty much impossible to attribute that to contamination. Next slide, please. All right, so this is all that data gathered up, and I'm plotting it against the yellow zigzag curve is actually solar abundances. So this is atomic concentration, and as you go from left to right, you're going from an atomic number of 2 all the way up to 98, so you're going all the way up to californium. That gives you a good idea of all the different elements that were detected and their relative concentrations. Next slide, please. So this is another way of looking at the data. I also plotted it as weight concentration instead of atomic concentration. And you can see that you see a lot of spikes forming in this thing, just like the solar data. And the reason why is because in solar nucleosynthesis, you get alpha particles being tacked on to carbon, which is a starting point in the nucleosynthesis chain when you get into the heavier stars. And the result is that every element is produced it tends to favor the even-numbered elements, and you get roughly 10 times the concentration of the even compared to the odd. That's called the odd-even rule of astronomy. I took that same mass spec data. What I did is an estimate, that's the lower curve, where I added in unmeasured isotopes because they had like a standard set that they would measure, but they didn't measure all of them. So I made a rough guess, and what I did is I added in both primordial and unmeasured stable isotopes for all the elements and gave them the same average concentration that was measured. And what you end up seeing is a very distinct pattern of the zigzag pattern forming, especially like in the rare earths, like to the middle right of the thing. You can really see that it follows that pretty closely. The purple curve on the bottom is actually stony meteorite concentrations. And then you see a light blue curve too that matches all of my general data. That's the average concentration of those elements in the Earth's crust, but no material on Earth, number one, contains all of the elements. And none of them would ever contain it in the exact average concentrations. I think this is a result of cavitation in the oceans during the primordial bombardment, mass producing most of the elements that were heavier than iron. So it was being produced by these miniature supernovas caused by cavitation from asteroid impact with the ocean, leaving a trail of cavitation bubbles into the ocean. That went on for a billion years during the primordial bombardment. And I believe it mass synthesized most of the elements and contributed to the origin of life. Next slide, please. So now I'm actually showing you a close-up of the mass spec that it shows. The estimated includes the unmeasured, stable, and primordials. But what I'm comparing against the lower curve are actually fission byproducts of the heaviest elements. So you see distributions like the blue curves are for uranium, so you get like a bimodal distribution. And if you look up above that curve to the measured data of the transmuted material, you can see that there's actually a strong signature of all those radioactive byproducts from fission. So not only was fusion produced, but the fission byproducts produce excesses of certain elements, like that really tall spike in the center is actually tin. And tin is the primary byproduct of elements heavier than fermium, because they tend to split into tin and tin, put them together, and you get fermium. And then the spike to the right, the blue spike there on the upper curve, that's lead. So there's a lot of lead, and that's the result of the tail end of uranium decay that was sped up by a neutron bombardment. And the curve just to the immediate right of the tin curve, that's barium, okay, and to the left of it is cesium and strontium. So, I mean, this thing is following the exact pattern of nuclear fallout. Next slide, please.
Transmuted material.
All right, okay, so now I'm showing isotope ratios because I measured individual isotopes for quite a few different elements. And so I took ratios of the isotopes that were measured, and then I analyzed the same ratios that are known for solar abundances. And what you begin to see is that, at least up as far as iron, it's very similar to the sun, but it begins to depart big time after that. Some of these isotope ratios are more than 10,000 or close to 10,000 times different than the solar abundances. So it's pretty obvious that there's a very heavy radioactive decay signature with these isotope signatures, that they're far off from the solar ones because the solar abundances have had 4 billion years to cool off, and this stuff all came straight out of the oven. Next slide, please. Now, it turns out that the bulk of the transmuted material was carbon and oxygen, with maybe 20% of all the rest of the elements being present. And you can see a strong correlation between the amount of carbon and the amount of the other materials. So what I did is I plotted for an individual particle its carbon concentration on the x-axis, and then the concentration of all the other elements vertically on the y-axis. And what this shows you is there's an interplay between the carbon and especially like the oxygen, which is the next step along the chain in alpha nucleosynthesis from carbon. So as the carbon is depleted, the oxygen increases, and then some of the oxygen is depleted, and that forms the next heaviest elements, and so on and so forth, all the way up the periodic table. And what this is showing you is that it's got very similar behavior, in fact, identical behavior to the effective nucleosynthesis that occurs in stars. So the right half of this curve is typical of type 1 supernovas, which are like white dwarfs with the layers of an adjacent star, a binary star, collapsing onto them. Hits the Chandrasekhar limit, and then it explodes, right? And everything to the left of that is typical of type 2 supernovas, which involve heavy star collapse, like stars that have really a lot of mass before they actually form and then collapse. And those will form the elements heavier than iron too, along with other types of type 2 supernovas. Next slide, please.
Cavitation fusion.
Okay, so now we're kind of getting towards the end here too, so we're just about going to wrap this up. What I'm showing now is that cavitation is occurring in a lot of the other cold fusion devices, particularly like the Pons-Fleischmann experiment. You've got electrodes down into the solution that can form cavitation from the plasma that they actually have observed and reported occurring on the anode, and they see pitting there too. And so I'm proposing that cavitation is really the driver behind the Pons-Fleischmann results, that they were seeing fusion too, but it's being driven by cavitation from the Leclair effect, causing not only impacts into the electrodes, but it's probably generating some trenches there too, but they just never really, paid too much close attention to it. And then of course other forms of cavitation like ultrasonics. Now you're getting bubbles that are collapsing, but they're not forming a reentrant jet if they collapse symmetrically like the upper right picture shows. And jet impact is tens of thousands of times higher pressures than just bubble impact. And then the other type of cavitation is cavitating rotor stators. That's the schematic shown in the lower right. Those produce lots of cavitation bubbles, and they're generally going helter-skelter. The jets would strike the inside of the housing of the impeller. They'd strike the impeller. They'd go all over the place. And so what you've got is a lot of cavitation going on with these. And in fact, that's really what I use too for the basis of that first experiment. But I've done it with both laser-induced cavitation bubbles and from bubbles coming out of pumps. So it's a pretty robust phenomenon. It doesn't seem to much matter what's generating the cavitation. Next slide, please.
Cavitation reentrant jet.
Yeah, the original, kind of going full circle, is that I originally had the cavitation origin of life theory. I didn't even know the crystal existed when I came up with that theory back in 2001. It wasn't until 2004 that I discovered it. So there's been a lot of synergy between cold fusion and the origin of life, believe it or not. And in fact, it's not really surprising that they go hand in hand, because my theory says cavitation nucleosynthesis replaced supernova nucleosynthesis, because it is supernovas on a small scale, and that this synthesized all the elements that were necessary for life in close proximity to some of the other crystals, which actually assembled it into DNA, RNA, and protein. You get like a one-to-one correspondence for protein link up with the crystal with adjacent bonds, and a 2-to-1 for RNA and DNA. So the crystal is the perfect geometry to be the template for assembling these things. It also eliminates the chicken and the egg problem, is that it creates both the proteins and the nucleic acids together instead of one before the other. That's my theory anyway. So yeah, basically I'm saying that cavitation from impact of the asteroids and the comets was happening at such a tremendous scale that you couldn't get away from cavitation in the oceans for a solid billion years right at the beginning, and life formed during the primordial bombardment, not afterwards. Okay? So I think that the theory is really strengthened dramatically by discovering the 0 point produced fusion. It goes hand in hand with the origin of life, and I think that when you look at the reach that cavitation has, it begins to kind of make sense, and one theory supports the other pretty strongly, in my opinion. So I just figured I'd throw that out there, that there's some support in Mother Nature for what's going on, that the Leclair effect does happen in Mother Nature under the right conditions. Next slide, please.
Summary.
All right, so bottom line is that this thing produced a tremendous amount of hot water when we did the thermal experiment, the 2009 experiment. Yeah, I put out 2,900 watts of hot water and only 840 watts required to produce that. So 3.5 times more energy out than in. Not too bad for the first go around. And now I also have my theory, which helps me explain all of this. And I just want to point out that if my theory were too far off from reality, it never would have allowed me to scale up to these types of effects in the first place. So, either the theory is, the basic tenets of it are correct, or the bulk of it is. I mean, I know there's a crystal and I know that it's accelerating. We could probably argue all day long about what's actually causing the acceleration, but that much I feel certain about. And I also think that, the Leclair effect is really the basis for most of the positive results that they've been seeing in low energy nuclear reactions, and that, this is why you're able to get it with various materials, because I don't really think it really depends on the material that much. It doesn't matter if there's palladium or nickel or anything else. I was able to achieve the Leclair effect in glass, in wood. I mean, it really doesn't matter what the substrate is. It occurs just in pure water itself. In fact, one of the most powerful experiments I did with radioactive release didn't involve any core at all. It was just sending aimed reentrant jets through the water. So, it's able to produce fusion very robustly under all different types of conditions and with different substrates. And then, of course, lastly, I think the crystallized cavitation reentrant jet really is the missing link, and that, it explains how we all got here. So kind of strange to think that cold fusion and origin of life are linked, but they certainly are. And that's pretty much it. I thank you.
Yeah. Now, Mark, because we overran our time, we're going to take the questions at the panel discussion tonight, and Mark's going to Skype back in for that. Thank you so much, Mark. That was a terrific presentation.
Well, thank you.